So it is my pleasure to next introduce Greg Muller, who will be speaking about reciprocity for valuations of theta functions.
Thank you so much, other Greg. As has often been the case lately, I'm very excited to share some results with you guys, and equally crushed that I can't be there in person to sort of talk with you guys about this result and listen to some of your talks in person. But nevertheless, I am still thankful for this opportunity to speak with all of you all digitally, at least. So the project I want to talk about today, and before I get too into it, I should say, this is joint with Man-wai Cheung, Tim Magee, and Travis Mandel. But this is really the proof of something that I've personally been trying to prove for like 7 years, a result I've been very excited about. But as is often the case with proofs of results, the result is more interesting than the proof. So my talk is really going to focus on the result itself, which has been around in various forms since as early as 2003. So I think most of this talk is going to be trying to get you excited about the result. And so we're going to cover a lot of ground that might be familiar to you in various forms. Okay, but let's start at the beginning. So I want to establish some conventions about theta functions, but I'll do so at a very vague generality. So specifically, I want to fix a seed in some lattice M. And I'm not going to tell you what that is, but suffice it to say that if you pick your favorite skew symmetrizable matrix, there's some seed associated to that, which spits out a cluster algebra at the end of all of this. And the theory of theta functions, which we've already heard about a bit this week, associates to every element in the lattice some sum of basically a Laurent series whose coefficients count certain broken lines in a scattering diagram. I won't tell you what either of those things mean. The only thing that matters for the purpose of this talk is that it's some enumerative problem that spits out non-negative integers, and if I attach those as the coefficients of my monomials, I can cook up some Laurent series that'll turn out to be magically related to cluster algebras. So some basic results in this is that the sum is not always finite, but if it is finite, then clearly it's a Laurent polynomial. And more relevantly to us, if we start with the seed of a cluster algebra, then we can get all the cluster monomials as finite theta functions. And more so, these theta functions extend to a basis of an algebra that is very often the cluster algebra, but occasionally it's a bit bigger, so sometimes it's called the middle cluster algebra. But the main takeaway is that these theta functions span an algebra with non-negative structure constants that contains the cluster monomials. Some fine details. I'm leaving the definition of seed vague, and I said for now, but I didn't even have time, so I will leave it forever, or at least until this paper appears. I will also say theta functions, the definition depends on a choice of base point, and I will say the base point is always in the positive chamber, so I will just sort of ignore the base point, the choice of base point entirely. Okay. So with those conventions established, I wanted to show you guys some examples that'll be more familiar in the cluster language. So if I take the following familiar skew symmetric matrix, I can think of this as a seed in this language of theta functions, and I get some enumerative problems in a scattering diagram. And if I actually count those broken lines, whatever they are, if I start with the initial vector m is equal to 0, -1, I'll get 3 broken lines, which gives me this Laurent polynomial. And if I rewrite it in terms of x1 and x2, I'll get this much more familiar Laurent polynomial that you recognize as one of the cluster variables in the A2 cluster algebra. Similarly, if I take m equal to -1, -2, I get quite a bit more broken lines. That gives me this big, long Laurent polynomial. But if I'm clever enough, I can factor it and realize that it actually just looks like this monomial in cluster variables. That is a cluster monomial. And because this particular guy is finite type, every theta function will be a cluster monomial. There's actually a bijection between cluster monomials and theta functions whenever it's finite type. But that's a special thing that only happens in finite type. So there's a very simple case. So there's nothing really that new under the sun. All right, so we've got theta functions, and I want to establish the other character in our play. And so to do that, I'm going to start with this. So we have this lattice M. And as is customary, we'll denote the dual lattice N, which is just going to be the set of group homomorphisms to Z. And given any element in this dual lattice, I can define a valuation on the Laurent ring, which I'm going to call val sub n, which just is going to take any Laurent polynomial, and it's going to go to all of the monomials present in that Laurent polynomial, apply the pair it with the element in the dual lattice, so apply that homomorphism to it, and then just take the minimum of the integers that appear. Okay. So in practice, m will often be identified with z to some power, and so we can identify n to z to the same power with the pairing given by the dot product. Okay. So in this concrete case, we can consider monomial valuations of this specific theta function. So the n is going to be identified with z2, so an element in the lattice n is just going to be two integers, n1 and n2. And then this valuation is going to take this vector here, take its dot product with each of these exponents, and just ask what's the minimum integer that appears. And so we get this function that's going to be the minimum of 3 integers that depends on our choice of n. So these are pretty straightforward. I'm calling them valuations, which I won't define, but suitably defined, these are a type of valuation on the ring of Laurent polynomials. And the takeaway should be that these are pretty easy to compute, right? If I have a Laurent polynomial written in terms of its exponents, I can just sort of inspect the exponents that appear, take a bunch of dot products, and find a smallest integer. Okay. So kind of the very basic setup for this is that we now have a family of theta functions parameterized by m, and we have a family of monomial valuations parameterized by the dual lattice n. Okay. But most importantly, we can pair these two. I can take any theta function, which is a Laurent polynomial, or at least a Laurent series, but often a Laurent polynomial. And then I have a valuation on Laurent polynomials. So I can plug one into the other and get an integer. Okay. So the question I want to think about today is, what can we say about monomial valuations of theta functions? And specifically, I want to think about these as functions of m and n. How do they depend on the choice of this vector m and this vector n? Okay, I think that'll give us some visual intuition for what's really happening here. So let's start by fixing the theta function. This will definitely be the easier side of this picture. So if I fix the theta function, then I've really got a fixed Laurent polynomial. And then I'm just looking at all the monomial valuations of this Laurent polynomial. But as we just saw a few slides ago, this really just takes the fixed set of exponents that appear, takes all the dot products with it, or all the evaluations of your vector with it, and finds the minimum one. And so it's easy to convince yourself this really only depends on the convex hull of the monomial, of the exponent vectors that appear. That is the Newton polytope. Okay. So if you cook up the Newton polytope of your theta function, then the valuation will just take the, will be given by a functional, and it'll just evaluate the functional everywhere on this Newton polytope and find the minimum value. And so depending on where n is in the dual space, you'll get one of 3 values. Okay. And so we get this nice piecewise linear function that tells you what this valuation is. So there's a couple of things to take away from this, aside from that it's pretty easy to compute. The first is that these two pictures are exactly equivalent information, right? Like a piecewise linear function like this completely determines the Newton polytope and vice versa. But both of them are potentially weaker than the theta function, because the theta function also knows what precisely the coefficients are and which monomials inside this Newton polytope actually have a coefficient. So these are equivalent pictures, but a little bit weaker than the information in the theta function itself. The other thing to take away is that this function, which sends a theta function to its that sends an element n to its valuation, can be thought of as the tropicalization of the theta function. That is, it's going to take the every plus that occurs and replace it by a minimum, and every product that occurs and replace it by a plus. Okay, so you may have seen this in a bunch of various results in cluster algebras where you take a Laurent polynomial and you tropicalize it. You replace various operations by these, you sort of demote them along this sort of tropical ladder. Okay, and that's precisely what's happening here. So here's another example. I picked that slightly bigger theta function. Now we have a quadrilateral Newton polytope, and so we get a slightly more interesting tropicalization. So this has 4 faces, so this has 4 domains of linearity, but ultimately still a pretty simple function. Okay, so that was fixing the theta function, but what if we fix the valuation and let the theta function vary? So at least a priori, this is a much harder problem. You need to be able to compute all the theta functions for all n. And this is generally a pretty difficult thing to do. While theta functions have a nice clear definition, outside some very special seeds, it's a pretty difficult thing to compute even a specific theta function, much less all of them. Okay. Also, a priori, there's not really much relation between different values of m. You can cook up some stuff and you can show some nice results, but generally you should think of this as a difficult problem if I just threw it at you, okay? But if we take some nice seeds where we can compute all the theta functions, for example, the running example of this A2 cluster algebra, then you can actually compute this, and you'll notice something funny. You'll notice that they look, first of all, like piecewise linear functions, and second of all, very familiar, okay? So here I've taken the running example, and I fixed two vectors n, and I've let the theta function vary over all possible m. And I'm going to get a function of m, of course, and you see that we're going to get piecewise linear functions, and these piecewise linear functions look very similar to the previous functions, okay? So what this suggests, and is true, is that these functions can be realized as valuations of theta functions in some other cluster algebra, some other seed, okay? So for example, here is the valuations the piecewise linear function we had on the previous slide, and we can realize it as valuations of anything with this Newton polytope, okay? And in fact, we can take this seed, so instead of the A-type seed, which is what you usually talk about in cluster algebras, there's this dual seed, which you can call an X-type seed associated to the transpose of the original matrix. And if you do this, you get a new problem with new enumerations, and you get new theta functions, and their tropicalization gives you precisely the piecewise linear functions we're getting before. We can see that if we get this guy here, we get, again, this function here. So all of this is suggesting that if we let the valuation vary, if we fix the valuation and vary the theta function, we can swap the two and find a new theta function whose tropicalization gives us that function. And it turns out this is a general phenomenon. So this is what I've been calling theta reciprocity, since we have this kind of pairing between elements in m and n, and there's kind of two ways to do it, okay? So here I'll give the statement. So we'll start with a skew symmetric seed, and here's an important disclaimer is while this statement makes sense in general and is believed to be true in general, our proof very much only works in the skew symmetric case. There's some fundamental issues in the skew symmetrizable case that don't manifest themselves in the skew symmetric case. But if you have such a seed, then for any element in the lattice m and any element in the lattice n, well, I can first cook up a theta function associated to m, and then take its monomial valuation, and this is some integer, or I can take n and cook up some theta functions in what's called a mirror dual seed, and this is a precise definition that appears in, for example, Gross-Hacking-Keel-Kontsevich, and this gives me another theta function in some different algebra, and I can take its valuations with respect to m, and the claim is that these are always the same. Okay, so this gives us this kind of miraculous way to turn this problem, which is very asymmetric in difficulty, right? Like cooking up a theta function you should regard as a hard problem. It involves this enumeration of broken lines, which generally is pretty difficult to do. But applying a valuation to a Laurent polynomial is just as easy as glancing at the support, okay? So it takes this problem with very asymmetric difficulty and swaps the two, which means that, for example, if I wanted to understand what this looks like for fixed n, so as a function of m, I can instead just compute, for fixed n, I could compute the dual theta function and tropicalize that, okay? So this reduces problems from computing all theta functions to a single theta function, which is often much easier, especially if it's a cluster binomial. Some remarks about this result. So first, this was conjectured originally in Gross-Hacking-Keel-Kontsevich, who succeeded in proving it when either of the theta functions are a cluster variable, or I guess a cluster binomial is the better thing to say there, but did not show it in general, okay? As I mentioned, the skew symmetrizable case should still be true. It's true in all the examples we can do, but there are some fundamental differences in applying our proof. And something that's actually pretty surprising is this even holds for infinite theta functions. That is to say, my definitions are a little poorly founded because if this is an infinite theta function, then it's not actually a Laurent monomial, but you can extend the definition appropriately. There's still some support to this infinite series, and you can just take the infimum of this functional over that support, okay? So, and if it's unbounded and your functional is going the right way, maybe that's negative infinity, but the theorem still says it's going to be negative infinity on both sides, okay? So this is remarkably seems to still hold true even when the theta functions are infinite. All right, so I wanted to show, there's a bunch of nifty applications to this, but one really quick one is cooking up for denominator vectors, okay? So for example, if I take any theta function in our running example, that is any cluster binomial in the A2 cluster algebra, I could of course write it as a Laurent polynomial in the initial cluster, and specifically write it as a rational function, right? A polynomial over a monomial. And so you can ask what powers appear in that monomial. That is, what is the denominator of this rational function? And this question, of course, can be rephrased as the value of this monomial valuation, because you're just going to each exponent and asking what the smallest dot product with 1, 0 is. This will tell you the smallest power of x1 that you need to clear the denominators here, okay? But by theta reciprocity, so here you'd have to compute all of the theta functions, which actually isn't too hard here, but this of course extends to other more interesting, more difficult cluster algebras. But for anything like this, you can use theta reciprocity to swap the two and make this a problem with a fixed theta function and a variable valuation. So you just have to compute this dual theta function, which you can compute as this polynomial here. I like to use y's in the dual cluster algebra, just to make sure you aren't confusing the two Laurent rings. And it also tends to match a lot of the earlier examples of this kind of tropical phenomena. But once you have this theta function, which will look like this polynomial in y's, its valuations with respect to m is just going to be the same as the tropicalization, right? I replace each y with the corresponding m, each product with a plus, and each plus with a min, okay? And so we get that the denominator of any theta function in this particular example is going to contain x1 to the specific power. And this is, of course, known basically since the beginning, because it's obviously a very easy cluster algebra to work with. But this kind of thing can now work in any skew symmetric cluster algebra. It says there's a specific dual theta function you can find such that its tropicalization tells you all of the denominator vectors for all different theta functions, okay? So very similar tricks can be used to cook up formulas for G vectors, opposite G vectors, and I mean, mutation maps is probably confusing since lots of things are called mutation, but specifically what I mean is if you have your scattering diagram and you want to change your initial seed to any other seed, there's going to be some piecewise linear map from that space to itself, and the coordinates of that map are going to be given by tropicalizations of dual theta functions, by theta reciprocity, okay? So a lot of these formulas have been known to be sort of tropicalizations of polynomials for a while, and in many cases either known or conjectured to be tropicalizations of dual cluster variables. And this is sort of the most general version of this phenomenon, or at least in the skew symmetric case.
Sorry, can I ask a quick question? So can you be more precise about this mutation map? A small example or whatever. Yeah.
Yeah, so for example, a one-step mutation. So you have a cluster algebra, you fix an initial seed. This gives you a scattering diagram in which you're doing this enumerative problem. And so you have this initial seed, and let's say you want to replace that initial seed with one of its mutations, a one-step mutation, say at I. Now we know that this is going to be given by some specific formula where you reflect across the ith hyperplane and then you shear each of the two half spaces by some amount. This formula is in Gross-Hacking-Keel-Kontsevich, for example. But what I'm claiming is by theta reciprocity, the coordinates of that map are also given by the tropicalization of certain dual theta functions.
The theta functions that you are talking about are actually the new class variable and you tropicalize it? Do you mean that, or?
No, the coordinates. So the picture I was talking about is sort of in the all taking on place on one side, and so you're tropicalizing theta functions in this mirror dual seed, which is not necessarily going to be a cluster algebra in the Fomin-Zelebinsky sense. It's one of these like dual cluster algebras. Defined by an X seed, and oftentimes it is a cluster algebra, but not necessarily.
Okay. And for calculating the G vectors, actually you need the Fourier condition, and you use the linear pairing using the Lambda matrix or whatever like that.
Yeah, exactly. Yep,
Okay,
those are both true.
I understand.
Yep, exactly. And the
Yeah,
opposite
thanks.
G vectors are the same, except there's a Donaldson-Thomas
Yeah, I
in
understand.
there.
Yes,
Yep.
thanks a lot.
All right, sounds good. Okay, so that was meant to be the description of this phenomenon where you have a choice of fixed cluster. But this phenomenon has an equally valid description that's sort of cluster independent that I wanted to give because I think it might be more familiar to some people as well. So I wanted to restate a bunch of the things I said in ways we know that don't depend on a choice of clusters. And so the first thing is I want to first just assume that all the theta functions are finite. That'll avoid some cases and simplify a bunch of my statements. So we're passing to a smaller case, but still covers a lot of interesting examples. Once I do that, I can consider the non-zero, the positive linear combinations of the theta functions on both sides. I'm going to call this A plus and A plus check, okay? So because we have the positivity of the structure constants, these are both semi-rings, right? You can add two elements and you can multiply them, but you don't have subtraction, you don't have division, okay? So something that's easy to check is that each monomial valuation restricts to a semi-ring homomorphism. That is, it turns plus into mins and products into pluses. This is basically a restatement of the phenomenon I observed before, that this is tropicalizing theta functions, okay? Okay, but the semi-ring homomorphisms of this form have come up a lot in cluster algebras in various ways. And so I'm going to denote the set of all such semi-ring homomorphisms as follows. So I'm going to let X of Z min be the set of semi-ring homomorphisms from the theta positive semi-ring to Z min. And similarly, X check is going to be the semi-ring homomorphisms on this A check algebra. The notation should be a little weird, and it's sort of alluding to the geometric story, which I'm avoiding overall. But if you let X be the spec of A, then these are cluster varieties with a positive atlas, and they have some notion of positive points or tropical points in the second set of sense of Fock-Goncharov. And that's precisely what's happening here. Equivalently, you could define these as weighted boundary valuations, which is how Gross-Hacking-Keel-Kontsevich defined these guys. But no matter how you define it, you're going to get the same set, at least with this assumption that all the theta functions are finite. So a simple observation is that the map which takes M to its monomial valuation identifies this lattice with the set of all semi-ring homomorphisms. So that is, every semi-ring homomorphism is some monomial valuation. Okay, so this takes this cluster-dependent lattice M and identifies it with this cluster-independent piece of data, the set of semi-ring homomorphisms, or the set of tropical points. Okay. Now this theta construction, this theta function construction, which before took elements in M to Laurent polynomials, can now be thought of as a map from this set here, which doesn't depend on a choice of initial cluster, to this algebra here, or the semi-ring here. Okay. And so this is the invariant way to define the theta map. This map doesn't depend on a choice of initial cluster, and so this gives us a nice invariant description of this theta function construction. This is kind of the heart of the Gross-Hacking-Keel-Kontsevich idea. All right, and so in our language, it takes val m to the theta function associated to m. Okay, and of course, there's the same construction on the dual side, which we'll denote by theta check, which takes semi-ring homomorphisms here, which we can identify with the lattice n, to the corresponding dual theta function indexed by n. Okay. So this is the heart of kind of the Gross-Siebert program, which says that if we have a dual pair of Calabi-Yau varieties, log Calabi-Yau varieties, then certain valuations on one should parameterize canonical functions on the other. And that's what these two maps are doing. They're taking boundary valuations on one to theta functions on the other. Okay, so this is sort of the cluster invariant description of these constructions. But from this perspective, we now have two very natural ways to associate an integer to a pair of two such semi-ring homomorphisms or valuations or tropical points, whatever you want to think of these. So you can take these sets and each one determines a function on the other, right? So I can take the valuation u and apply it to the theta function determined by mu, or I can take the valuation of mu and apply it to the theta function determined by mu. So geometrically, I should have these two varieties, and special valuations on each of them should determine functions on the other. But that means if I have a special valuation on each of them, then I have two ways to pair them. I can take the first one, and get a function on the second and apply that valuation here, or vice versa, okay? And so theta reciprocity is merely the observation that these two integers coincide, conjecturally in general, but provably in the skew symmetric case, okay? So this is kind of the intrinsic characterization of it, that we have this coherence of this pairing. And I should say, right, and so I like to give this a name. So kind of one of the main takeaways of theta reciprocity is that we have this one well-defined pairing, which we can think of as taking either m and n, or the tropical points on x and the tropical points on x check. However you want to identify these sets, there's this one well-defined pairing that takes that one in each to an integer that just takes either of these constructions. So it either cooks up the theta function parameterized by the second valuation and applies the first valuation to it, or vice versa, okay? And by this theta reciprocity theorem, these give you the same pairing, okay? So a nice thing you can say about this, which is equivalent to theta reciprocity, is that if you fix one of these two arguments, then the other argument extends to a semi-ring homomorphism on these should be A, not O, A plus and A check plus check, and every such homomorphism is of this form. So you can think of this as like being a perfect pairing, except for semi-ring homomorphisms rather than abelian group maps, right? So a perfect pairing between like vector spaces is a pairing where if I fix one argument, I get a linear map on the other, and all such linear maps are of this form. And here we just have the semi-ring homomorphism version of this, okay? And I should mention, none of this is new. Really, the only thing that's new, at least from my perspective, is the proof of this theorem. The existence of such a pairing goes as far back as 2003. Like if you look at Falk and Gontrov's paper on cluster ensembles, part of their whole Falk-Gontrov conjecture is the existence and coherence of such a pairing, really from their perspective inspired by examples from Teichmuller theory. Okay. Okay. So with the time I have left, which is not much at all, I wanted to give an example of kind of this theta pairing, this invariant perspective, in something that's hopefully familiar to most people here. That is the n-gon. Okay. So if I consider a disk with at least 3 marked points on the boundary, then we know the cluster algebra is equivalent to the skein algebra of arcs between marked points. And I guess I should say I'm considering with frozen variables associated to boundary arcs. So this is a rank 7 cluster variable, so I'm not just deleting boundary arcs. Okay. So there's this nice skein description of this cluster algebra. And therefore, we can parameterize the basis by non-crossing multi-arcs between marked points, right? That's the topological, the combinatorial data that determines the basis. And then we can map them to special elements in the cluster algebra by just identifying them with elements in the skein algebra. Okay, so we have this map theta, which sends non-crossing multi-arcs to the corresponding elements in the skein algebra. One bit of fine print, because I'm allowing frozen variables at the boundary, and I do want to localize my frozen variables, I do allow inverses to boundary arcs, which I denote in red. I don't think it'll matter too much, but that's what's meant here. So you can think of all of these as multi-arcs, which are determining elements in the skein algebra. Okay, so that's a familiar part of the story. A less familiar part of the story, for some, is as follows. So I want to consider unmarked arcs, arcs that go between parts of the boundary that are not marked points, up to homotopy. And then I want to distinguish a class of multi-arcs that I'm calling even, which are going to be those that intersect every marked arc an even number of times. So for example, take this multi-arc here. No matter what way I connect any 2 marked points, it'll intersect this picture an even number of times, okay? So that's a special trait I might ask about marked multi-arcs. That's not true of these guys, right? I can draw arcs in both of these pictures that intersect these arcs an odd number of times, okay? Again, I allow inverses to certain boundary arcs. So my claim is that the dual cluster algebra here is naturally identified with the subalgebra of the skein algebra generated by even unmarked multi-arcs. Okay, so this first claim is that this is a closed, this is a well-defined subalgebra of the skein algebra. And then the second is that it's really what happens if you apply this dual construction here. Okay, but the theta pairing is then easy to describe. I now just want to take a marked arc or a marked multi-arc and one of these even unmarked multi-arcs and associate an integer to them. And my claim is that I can intersect them or count intersections. And by this even condition, it's always going to be even integer. And my claim is the theta pairing is always -1/2 the number of intersections. Okay. And this is, of course, in the disk, but interestingly, this extends to non-punctured surfaces in sort of the obvious way. And so I just have a simple example here. So you'll recall that you can use tropicalized dual theta functions to measure denominators, right? So for example, if I call this element here x, and I want to take some other element in the cluster algebra and compute what its denominator is in any cluster containing this x, then I can cook up the following theta function, the following dual theta function. This is a theta function in that dual cluster algebra, which can be denoted by the following topological object, and red again means a negative power. And if I want to take then any arc or any multi-arc in the cluster algebra, I just intersect it with this, and then I do 1/2 the number of intersections, and that'll tell me the denominator of that Laurent polynomial. So you can check that, like for example, these guys will both have 1, they'll intersect twice, so half that is 1. They'll have just 1 power of x in the denominator. Anything compatible with x will have 0 intersections, so it'll have no powers of x in the denominator. And x itself will have, well, technically x to the -1 in the denominator. But yeah, and so this is something that fully generalizes to other surfaces. You can always draw these pictures that completely measure denominators. And one fun takeaway is that, and this is something that's been proven other ways in other forms, is that these denominators are independent of the choice of cluster containing it, right? This statement did not choose a cluster containing x, okay? So this is just trying to sort of maybe get you a little bit excited about this theta reciprocity result, these pairings, and the fact that now every cluster algebra should have this canonical pairing with a dual cluster algebra that in many of our favorite examples corresponds to some nice construction. And I think that's my time.
Thank you very much, Greg. Again, I'll start with questions in the room.
We have one here.
Hi, Greg. Thanks very much. Can you say a little bit more about why you end up having to do this trick with even multi-arcs and half the number of intersections rather than just...
Yeah. Maybe the easiest way to say it is that the skein that these semi-ring homomorphisms from the positive skein algebra to Z are not generated by counting intersections with these unmarked arcs. So it's not hard to show that if I have an unmarked arc and I count intersections with elements in the skein algebra, this gives me one of these valuations, one of these tropical points. But the not every valuation is of this form. So maybe, yes, the motivation from the semi-ring perspective is that you need to make sure, you know, the dual cluster algebra is going to be parameterized by all of the valuations. Maybe a very different perspective, which maybe is more satisfying, is that in this particular case, we know that the dual cluster algebra can be embedded in the cluster algebra by an augmentation map. But this augmentation map is going to have order 2 to the number of marked points. And so we're getting, this is really where this identification is coming from. You can take, for example, any of these unmarked multicurves and rotate them clockwise until they hit a marked point, and this will give you a marked multicurve. And this will embed the dual cluster algebra into the cluster algebra. And this gives you the augmentation map, but it's giving you a proper subalgebra. And so this even condition is just kind of characterizing what that proper subalgebra is. I don't know if that answered your question.
In a sense, but I mean, it's as a sort of meta level, where does the 2 come from?
That's a good question.
Is it, could it be anything like kind of the pairing between a co-root and a root, or something mad like that? Or I mean,
sort of. So I think
what is 2?
I mean, I think if you were to ask, for example, Falk-Goncharov, at each of the marked points on the X side, there's slightly more information being chosen than on the A side. And it's a 2-to-1 factor. So 1 is going to be an element in the tautological representation of SL2, and the other is going to be a point in the light cone in 1,2 Minkowski space, and there's a 2-to-1 covering from each of them. So if you pass from one moduli space to the other, there's going to be like a finite sheeted cover. and on the level of functions, this should be where this 2 is coming from.
Is that like this the center of SL2?
Yeah. I think.
Okay, that's probably enough for numerology. Thanks very much.
No problem.
There are no questions in the room at the moment.
Okay, we have a few questions in the chat. Salvatore Stella asks, can you elaborate on what goes wrong with the skew symmetrizable cases?
Boy, howdy, can I. Sort of the essential trick in our proof is that the mirror dual cluster algebra is not quite the same as Falk-and-Goncharov's cluster dual cluster algebra. The two constructions differ by essentially the transpose of the exchange matrix. And so if the exchange matrix is skew symmetric, then your two constructions really just differ by a sign. Essentially, you reverse the directions of all the arrows in your quiver. And so that's pretty easy to reconcile. In fact, those two algebras are going to be isomorphic as long as there's a green to red sequence, maximal green sequence, whatever. So the cluster dual in the sense of Falk-and-Goncharov and the mirror dual in the sense of GHKK are almost the same. They basically differ up to sign in the skew symmetric case, but in the skew symmetrizable case, the transpose of B and the negation of and B itself aren't just differ by a sign. And so in fact, the two guys are going to have non-isomorphic cluster algebras. The only reason the conjecture still has a chance of being true is that the tropicalizations of these should still be the same. So we have this kind of conjecture that while we have genuinely different sieves that give genuinely different algebras, that they should still have all the same tropicalizations. The Newton polytopes should all be the same. And that's still a thing to show. We don't know how to show.
And next we have a question from Nathan Reading.
Nathan?
Very interesting talk. I just wanted to follow up on Fan Chin's question about mutation maps. So if I understand right, you answered in the one-step case, but if I understand right, you could give some sequence of mutations, and then the content of, if I understand right, the content of what you're saying is that by tropicalizing some theta function that lives somewhere, you could sort of give all at once this piecewise linear map, breaking into cones and saying what the map is on each thing somehow all at once. Is that right?
Yeah. Yes.
Very cool. Thank you.
Yeah, no problem. I think it's going to be, you take something like the C vectors, you take the thing you want to be your new initial seed, you look at the C vectors, the inward pointing normals of the walls, you look at the dual theta functions determined by those C vectors, and then up to a sign and maybe a twist, it's just the tropicalization of those guys.
Thank you.
Any other questions from the room or Zoom?
So I have questions. So Greg, so how do you prove that?
Oh man, I could talk for a whole hour about this. So you can embed this problem in a full rank problem. So we assume full rank and we pass to a quantization, and then it's actually kinematics of broken lines. So whenever you have a compatible quantization lambda, there's a conserved quantity of broken lines that we call the lambda momentum. Basically the pair, if you use lambda to pair the position and the derivative of broken line, you get a number that doesn't change when the broken line hits a wall. And so we call this the lambda momentum because in the plane, lambda is just a multiple of 90-degree rotation. So it's just going to be a multiple of the angular momentum. And if you know the greedy equals theta paper, the key result there is that angular momentum around the origin is conserved by broken lines. So we have a more general phenomenon. Whenever there's a compatible quantization, the lambda momentum of broken lines is conserved at all time. And then we have this fun characterization that the tropicalization of a theta function, the value of a tropicalization of a theta function at any point, is just the smallest lambda momentum of any broken line that ends at that point. And so this allows us to rephrase what tropical theta functions are in a much more kinematic way. And then we use, basically we need theta reciprocity reduces to, if there's a theta a broken line with this lambda momentum, then there has to be a broken line that over here that does this lambda momentum. And then there's a sort of a transformation on broken lines due to Tim, Mandy, and Cerulli-Arelli that does it. But yeah, the main thing is looking at lambda momentum in cases where lambda exists. Yeah.
I see. Great. Thanks. And yeah, maybe I have a comment. So actually, so Travis, a few days ago, he asked me, but I didn't got the time to say that. So in literature, so people have been, I mean, actually, Jerry Fay, he has studied the pairing using the generic basis. And there are some, I mean, he cannot do it in full generality, but he has developed some representation theory formula for the pairing using the generic basis. And for the moment, of course, we do not know if these two different bases give you the same pairing, but of course, you can believe that that is the case. And in particular, if you look at the surface type, so the Bangles and Risley, they are not so different. So yeah, if you count the intersection, the different bases should give you the same valuation pairings.
Yeah, yeah. So to sort of restate what Fan is saying, so something I sort of buried at the beginning is that these tropicalizations only depend on the Newton polytope, and so they're pretty insensitive. Some of the choices make.
Yes.
So there's actually different bases beyond the theta basis that should have the same tropicalization.
Yeah, we always conjecture that, but yeah, I never know how to prove that.
So while I defined this theta pairing, it's possible that this pairing doesn't really depend on the choice of using theta to define our basis at all. You know, this might be the exact same pairing if you used bands or bangles instead of bracelets.
Yes,
for example.
Yeah, thanks.
No problem.
I don't see
Greg,
any other questions, so let's thank Greg again for a very inspiring talk.
Thank you kindly.
And we will, let's keep it as a 5-minute break. So we'll start at 32 after.